Now that we have a handful of integration techniques under our belt, I want to focus on some more applications of integration. And the first application that I want to look at is arc length. So arc length is simply what we call the length of a curve in space as you sort of follow all the bends along the entire way. So for example, like a circle, if you think of the circle as a curve in space, the arc length of the circle is the same as the circumference. It's the length around the edge of that curve, in a sense. So arc length is simply the length of a curve in space. We are going to focus on ones in 2D planes here, but this can actually be extended into 3D, and that's something that you'll probably see when you take Calculus 3. So I should mention, let me just write down that circle example as well. So for example, the arc length on a circle is the same as its perimeter, or its circumference, I should say. Right, so on a circle, that's 2 pi r. Clean that pi up a little bit here, 2 pi r. And so that's what we mean. We're following the curve as it moves around. But we can generalize it to other shapes as well. So for example, if I draw a curve, let me locate a curve in the xy plane here. So here's my x and y axis. And I've got some curve doing whatever it's going to do. Right, so here's some curve, some y equals f of x. So we have an equation for this curve. And maybe I want to find the arc length between x equals a and x equals b. So I want to go from this point up here all the way to this point right here. So these 2 points, I want to find this distance. We can approximate this length so approximate in this case the arc length of our function, which is y equals f of x, between those 2 points, so between x equals a and x equals b, by basically breaking the interval up into a bunch of segments and so sort of chopping it up and adding up the lengths of each of those corresponding little segments. So we can approximate it by, let me get rid of that comma, by breaking the interval up into pieces. And then adding up the lengths of those corresponding pieces. What am I trying to write here? Lengths. Okay, so what do I mean by that? I mean, we're going to basically chop this up into a bunch of points. Let me put a bunch of other points on here. That'll be enough. We'll call this first point P0, and the next one will be P1, and then P2, and so on, all the way up to some Pn, the last point. And somewhere in between all of these, maybe we'll have a point that is P sub I. We'll have the one past it, P sub I plus 1, and the one before it, P sub I minus 1. And so that's kind of how we'll refer to these various points, is basically a P with a subscript indicating which point along the way we're sitting at, starting with 0, going up to n. So we've chopped it up into n pieces in this case. What we're going to do is, instead of actually trying to find this smaller arc length, that's basically the same problem that we're still having. It's still a curved length. But if we can instead approximate it using just a straight line, and then a straight line again for the next one, and then a straight line again for the next one, and a straight line, and a straight line, and a straight line, and so on and so forth. If we break it up into a bunch of straight lines, we can essentially just use the distance formula to find all of those individual lengths of all the pieces. And then if we apply calculus, take the limit as the number of points that we're using goes to infinity, our approximation is going to become exact. And so that's kind of the idea that we're going to follow here, is we're going to, instead of following the actual curve, we're just going to find straight line distances. I don't know how to find a curve distance, but I do know how to find a straight line distance. So we're going to find that straight line distance, and then we're going to apply a limit to let the number of points that we're using in our approximation go to infinity, and the distance between the points go to 0. And that will make our approximation exact. So what we're really doing is adding up the individual lengths of these line segments, I should say. So it's not their individual lengths, it's the individual lengths adding up. Just the way I can edit this the least. The individual lengths of the line segments. That's a better way to put it. So of the line segments, connecting all the points. The points being the points that we use to break up our interval. So that's going to be our idea. So the idea is our arc length, and the letter we're going to use for arc length will often be L if we're talking about the total length. And you'll also see the letter S get used a lot when we're talking about sort of arc length as a function, as sort of a variable, usually a lowercase s. But here the total length is going to be basically the limit as n goes to infinity, so n being the number of our intervals, from the sum from I equals 1 to n of the length between pi and the next point. In fact, I'm going to follow the same notation the book uses. They do pi minus 1 up to pi, which is what I need in this case, based on the way that I labeled these up here. Okay, so why am I using the I minus 1 and why am I starting at 1 and going to n instead of 0, right? We had a 0 up here. Well, this is exactly why. I'm going to think of this first interval here between p0 and p1 as interval 1, and this interval here is interval 2. And the lengths of the first intervals, if I look at this, when I equals 1, that needs to correspond to the first interval. And when I equals 1, the points that I'm going to be looking at are going to be p of I minus 1. So if I is 1, when I subtract 1, it'll give me 0 here, and pi itself, which will be 1. So it'll be the distance between p0 and p1. So let me just write that down, where this notation is meant to indicate a length. So pi minus 1, pi, in these vertical lines that look like absolute values. That's essentially what they are. They're magnitudes. It's a way of writing distance. But this is the straight line distance. So I'm just going to write that as distance between the 2 points. So between pi minus 1 and pi. So again, when we plug in I equals 1, it'll give me the distance between p0 and p1. When I plug in I equals 2, it'll give me the distance from p1 to p2. When I plug in 3, it'll give me the distance from 2 to 3, and so on, all the way up to n, where it'll give me the distance between n minus 1 and n, so the point before the end and the end point. And these are just going to be all the straight line distances. we're summing up all the straight line distances, but we're also now taking the limit as the number of these straight lines that we're using goes to infinity. And that necessarily means built into this n getting big, these distances are going to be getting smaller and smaller and smaller. These distances will wind up going to 0, and we'll see that a little bit later on. Okay, so this is going to be our definition of how we compute these lengths, but now we need to go be a little bit more careful with this term right here. So thinking about what this represents, this p sub I minus 1 pi, try to write it as carefully as possible so the subscripts don't get buried. This is just going to be the square root, right? So I'm doing the distance formula of the distance between, so the difference between the x coordinates of the 2 points. So I'll call that x sub I minus x sub I minus 1. So the x coordinate of point I, the x coordinate of point I minus 1 of our 2 points here. I'm going to take those two x coordinates and square them, and then to that I'm going to add the difference between the y coordinates. So this is just the distance formula, normal good old distance formula that we've seen a million times before. So that is how we're defining this distance here. It's the straight line distance. To make things easy, I'm going to write this as just delta x sub I, and this will be delta y sub I. So the difference, again, between the two x coordinates and the difference between the two y coordinates, we'll just call those the deltas. And when we look at our picture, kind of zooming in on a curve, what we wind up seeing is that if this is what the curve is doing, and here is the point p sub I minus 1, and over here is some point p sub I, then we can basically turn this into a right triangle type picture. So there's the right triangle. This distance right here is the difference between the two y values. So this is what we're calling the delta y sub I. And this distance here is what we're calling the delta x sub I values. And the hypotenuse is the length that we just found. So this hypotenuse, just keep it in mind, it's p sub I minus 1, p sub I. So this is the picture that we're looking at when we do this distance formula. It's essentially, the distance formula is just the Pythagorean theorem on a picture that looks like something like this. Obviously, the hypotenuse here is not identical to the length of the curve. The length of the curve is actually longer in this case, right? The shortest distance possible between these 2 points is a straight line. So generally speaking, the arc length will actually be longer than that value. But in the limit that the delta x shrinks, so that this point moves closer and closer and closer to this point, these two distances, the straight line distance and the actual curve distance, will wind up approaching the same value, so in that limit. And just to be totally clear, again, the coordinates of this point up here, this is the x sub I, y sub I, right? So it corresponds to this x coordinate, this y coordinate, and the one down here is the same thing, but with the subscripts of I minus 1 instead. So it's x sub I minus 1, y sub I minus 1. So there's the coordinates of those 2 points. That's kind of what we're looking at. Okay, so hopefully the big picture idea is clear, that all we're doing is, again, taking a limit of an approximation, and that limit makes it exact. But I want to go through the derivation of the arc length formula more carefully to see the one that we're going to actually wind up using. So this is not something I'd expect you to be able to reproduce on an exam or something like that, but I do want to be careful and go through and get to the formula we're going to actually use in a rigorous way. So I want to start as we try to derive the formula. Let's come zoom back in here. So to get the formula that we're actually going to use, which hopefully it's obvious that it's going to involve integration because we're in the applications of integration section, as I mentioned. We need to start with the mean value theorem. Hopefully you remember back, I mentioned the whole point of the reason that we were learning the mean value theorem was so we could use it later on to do things more rigorously. Well, here's that later on. Here's why we needed the mean value theorem before. So let me just give you a quick reminder of what the mean value theorem says. The mean value theorem says basically the following. So let me write it down mathematically and then just explain it in plain English. So it says that if I take this and this, so if I take the function evaluated at these two neighboring points, so these are basically my two y values, and then I divide them by the difference between the two x values, we will wind up with f prime of xi at some point somewhere on that interval. So, okay, what we have on the left is basically the average slope. So this is the average slope on the interval between our point p sub I minus 1 and the point p sub I. And we said that that average slope is equal to the actual slope at some point on the interval. So this is the actual slope at some point on the interval. And what interval am I talking about? Again, I'm talking about the interval between I minus 1 and I, so somewhere on here. So basically we're saying there is a point somewhere on here, maybe this is the x sub I value, so that with the star, there's the x value where the slope at that point matches the average slope, which is basically the slope of the hypotenuse of the right triangle. That is sort of our average slope, right? These are just our delta y's, right? It's this. These are this is our delta x. So if I take this rise over this run, we get the slope of the hypotenuse right there. So this is all we're arguing. There is a point somewhere on the interval where the slope at that point will match the overall average slope. That's what the mean value theorem says. So this is for some point x sub I star on the interval that we care about. And I've just drawn it into the picture up here. We don't necessarily need it, but that's kind of the idea. There is a point, assuming this is a well-behaved smooth curve, there will be a point somewhere between p sub I minus 1 and p sub I where the slope at that single point matches the average slope between the two values. And we're going to use this to just rearrange things. So I want to point out that, again, we just mentioned this is just the difference between the two y coordinates, right? The y value here and the y value here. That's our delta yi. And down here, that's the difference between the two x coordinates at these 2 points. That's our delta xi. And so if we rearrange these terms, we get the following. So I'm going to multiply basically both sides by this delta xi. So we get, on the left, we'll just have that delta yi. That'll be what's left. And it's going to be equal to f prime of xi star, some point on that interval, times the delta xi. So all I've done is take this formula right here, where I've swapped in for these two, the numerator and the denominator, I've swapped them for just something shorter to write, delta yi and delta xi. And then I took both sides of this and multiplied by delta xi. And that gives me this expression right here. To make life easy, let's let this delta xi be uniform for all the different points back here that we looked at. let's make all the x differences be the same. So basically I'm saying let's chop up our interval in the x direction into n equal parts. So I want all the delta x's to be the same. So let's let all the delta xi's be the same. And we'll just call it delta x that way. So it doesn't matter what value of I you're at, they're all just going to be the same distance. We'll just call it delta x. And that's what we will be doing going forward down the line. So with all of this in mind, what we get, going back to our distance, the notation we were using, the p sub I minus 1 p sub I, it was, as you recall before, coming back to this formula. So I'm going to combine two things. I'm combining the mean value theorem along with the way that we defined that distance as just being the hypotenuse of this right triangle. And notice that we also tied the mean value theorem into the hypotenuse of this right triangle. So it's going to play two different roles. So this is the definition that I'm coming back to up here. Just remind you what that looks like. This is just the Pythagorean theorem for this being the length of one leg and this being the length of the other leg, so delta xi, delta yi, that we wind up getting the length on this side being the square root of the sum of the squares. So that's what I'm writing right now. So this is just simply the square root of the sum of those two squares. So it's the delta xi squared term plus the delta yi squared term, whole thing square rooted. But now I can write them all in terms of this using the mean value theorem. So I can replace where we have the delta yi term, I can write it in terms of x's so that I'm not dealing with both x and y. I can write everything in terms of x's. So this is going to be equal to, and also using this fact that we're going back to just delta x's, I'm going to rewrite this as delta x squared. Right, we're dropping the I because I said that all of them are going to be the same, so let's just call it delta x. And the delta yi values will be replaced with this expression here. So we've got, put it in parentheses here, f prime of xi star delta xi, but we're replacing delta xi with just simply delta x squared. Right, so here's our delta xi squared, and here's our delta yi term squared, plugging in this representation right there. Okay, so notice both of these terms involve a delta x squared term. So if I were to square both of these, I can pull that delta x squared term out. And that's what I'm going to do. So I can rewrite this as pulling that delta, in fact, I'll leave it here at the end. So I'm going to pull the delta x squared term out, and that will leave me with this term just being a 1. And with this term, I'm just going to have the derivative, and this delta x will be gone. So I'll have plus f prime of xi star squared. And I guess we can even leave that in our square brackets to make it a little easier to read. And what I've pulled out was the delta x squared term, but it's still within the square root. So I've split this up. I've basically factored a delta xi out. In fact, if you want to think about it like that, maybe that's an easier way to write it. Oops. So I can think of it as, here's one piece, we pulled a delta x squared out of that. Okay. And lastly, to clean this up, this piece here that's being squared and then square rooted, I can treat separately, pull that outside the square root, and wind up with just the square root of 1 plus f prime of xi star squared. Oops. Times that delta x that's left over after we've both square it and square rooted. Okay, So I've got this new expression for this little length, the straight line length. This is our expression for the length of the hypotenuse in terms of, the only thing that we need to keep in mind is it's in terms of this slope, the slope at some point that happens to be somewhere in that interval. So far that's all we've got. We've written this distance in terms of only x's, no y's anymore, and the slope at this point that happens to be somewhere on the interval. I don't know where, but it's somewhere on the interval between I minus 1 and I. That is what we have right here. So the arc length is simply going back to the original definition. It's simply the limit as n goes to infinity of the sum of all of these lengths. And so that's what we're going to do now. So the arc length is L equals the limit as n goes to infinity of the sum from I equals 1 to n of all of the p sub I minus 1 p sub I lengths, which we now have written like this. So I'm going to rewrite it with that square root here. Okay. What is this? Well, keeping in mind that this piece right here, delta x, is just going to be b minus a over n. We'll remember that that is basically, again, just the length of the total interval divided by into our n equal parts. That's what each delta x is. It's going to be the total distance between a and b divided by into n equal parts. So b minus a is that length. Dividing it by n gives us our delta x that we're using. So we'll see again, this piece in here is going to 0 as n gets very large because we're having a constant over n. So as n gets large, the delta x is going to go to 0. And we're adding up an infinite sum of infinitely small things. And this whole thing, using our limit definition of the integral, becomes the following. It's the integral from a to b of the square root of 1 plus f prime of x squared dx. Okay, so what happened to the x sub I star? And this is the only thing that kind of hasn't really been explained. So this is our limit definition of the integral. Otherwise, if you go back to where we did the limit definition of an integral, this was back in Calculus 1, this is exactly what we wind up getting. Here's our limit definition of an integral. The only question is, what happened to the xi star? Why am I now just using x? Why was I suddenly able to drop that? Well, I want to think about what happens as n goes to infinity in this picture. We just said as n goes to infinity, so as the number of segments goes to infinity, the width of the segments, the delta x, is going to go to 0. And so if we kind of zoom down, imagine we're looking at this last one and we zoom down and are looking at it here now in this picture. As these points get closer and closer together, the xi star has to stay between them. But we're basically taking the limit as the point pi and the point pi minus 1 move together and become the same point. And so what happens to the xi star? It has to stay between them. It must just basically go to that same exact point. So if it's stuck between them, and this point's coming in this way, and this point's going in this way, and they're moving on top of each other, this necessarily stays between them, and eventually it will all shrink to one single point. That one single point is the point that we're just calling basically our xi. So let's take this one as it goes to that way. Maybe that'd be a better way to put it. So this is all going to go to our xi, and we can drop the star. And xi in our limit definition, once we drop off the I notation, right, we don't need the star anymore. So I've hopefully explained to you why we got rid of the star, and it's part of the limit definition of why the subscript I goes away. Right? This was always the way that we dealt with these limit definitions of integrals. But the star goes away because it's literally going to shrink down to a single point, xi. That's the only point we can pick. And so this is the formula that we're going to actually wind up using. So let me write this down. This is our arc length formula. Derived way more carefully than you probably care. And it basically says the following. So notice to get this all to work, we had to use the mean value theorem. And so this is going to require the same requirements that the mean value theorem required. So basically what it says is if our function f prime of x is continuous, so we need that the derivative to exist. So the original function needs to be continuous, and its derivative also needs to be continuous. So if f prime of x is continuous on the interval, on the interval from a to b, then the length of y equals f of x, the arc length, so to speak, on that interval is given by the following. L equals the integral from a to b of the square root of 1 plus f prime of x squared. So I'm going to put it in square brackets like that with the square outside just to make it totally clear. These things can get really weird if I just wrote it like that. It's kind of ambiguous or just ugly, so I'm putting in those square brackets just to make it clear that I'm taking the whole f prime of x and squaring it. So just keep that in mind. It's just a notational thing to try to make it as unambiguous as possible. And don't forget our dx. Another way to write this is if we use our Leibniz form of our derivative here, and this might be something that will be useful going forward. We can rewrite this alternatively. This sometimes is an easier one to remember for some people, but you can rewrite it as dy dx squared dx. So that's the same thing, right? dy dx is the same as our f prime of x, two different notations for our derivative here. One other thing I should mention is it's also possible, so this is just a quick side note, we have our function written as y equals f of x. What if we had a different setup where instead of solving for y as solved for as a function of x, what if we had x solved for as a function of y? So if we have x equals g of y instead, and occasionally this is more convenient. We've seen scenarios where integrating with respect to y in some cases is more convenient than integrating with respect to x in certain situations. So this is kind of just one of those situations. If it for some reason is more convenient to write our function this way, then the formula, so it's essentially the same conditions hold, but the formula is going to be the following. L equals the integral from a to b, or I guess we can use different letters because it's these a and b were in terms of x, from x equals a to x equals b. These will be in terms of y. So maybe our y starts at a height of c and goes to a height of d, times the integral, or sorry, times the square root of 1 plus our g prime of y squared dy, which again can be rewritten using Leibniz notation, which is the dy dx notation, but in this case it would be 1 plus, instead of dy dx, it's going to be dx dy squared dy outside. And so you may encounter situations where this formula is slightly easier to use than this one up here. Okay, so this is sort of the whole hypothetical. This is how we can actually find a concrete length between 2 points. In a little bit, we'll derive something called, it's going to still be an arc length. It's going to be related to arc length, but it's actually going to be a function. We'll keep a variable in there. So we'll, it's kind of the equivalent of instead of finding a definite integral, finding an indefinite integral. In a sense, it's kind of the analogous way. But for now, let's do a couple examples of this, but then I will show you later on an arc length actual function that we can use where we don't necessarily have to specify a and b. I can say, let's go from a to any point of our choosing. We can call this upper bound, s or t or something like that. Okay. So, but before we do that, let's get a little comfortable with this. And just to review, because this is a complicated thing, so I don't want to make this more confusing. I don't want to scare you with all the work that we did, but ultimately, big picture idea, all we're doing is finding this total length here. These formulas way down here that are now too tiny to read just come from taking the process that we just did. We're just going to find the straight line distances between all of our individual points on our curve. So find a bunch of straight line distances and add them all up, and then take the limit as the number of segments that we use goes to infinity and the length of them goes to 0. That's all we did. So it's all just Pythagorean theorem. We use the mean value theorem, which is basically another way of reframing the Pythagorean theorem in this particular case, and kind of combine those two together to get these formulas that we're going to actually use in practice. So that's where these formulas came from. Now that you've seen them derived, I'm not going to make you rederive them, but hopefully it's not too confusing where these come from. And I can even do, well, yeah, maybe this is an appropriate place to do this, sneak this in before we do an example. How do we remember these formulas? So how can we remember these formulas? Let's start with that first one. So for example, if L is equal to, I'm going to do the Leibniz form, so the dy dx form. One way to think about this is what we've really got here, in a sense, is, and this is going to kind of be abusing this notation. So this is, we're cheating in a little bit, but this is an easier way to remember it. We just had a picture of our triangle that looked vaguely like this. We had a delta x here, we had a delta y here, and this length is essentially the length that we're approximating over here. And you could almost think of this as being kind of our A and our B, so to speak, our x coordinates A and B at least being over here and over here. So let me maybe do it this way. So again, I'm kind of cheating here just a little bit, but this will hopefully make it kind of clear how this all fits together. It's all the Pythagorean theorem. We clearly have that L should be equal to the square root of delta x squared plus delta y squared. And what happens if I, within this, factor out basically a delta x squared, if I force of delta x squared out of this? So let's force out a delta x squared. So there's not a delta x squared to be factored out, right? It shows up here, but it does not show up here, but we're going to force it out anyways. So what I'm going to do is rewrite this as delta x squared. I forced it out. That first term has a 1, and the second term is going to now be delta y squared over delta x squared, which you could see if we redistributed this back through. I'd get the delta x squared term as the first piece, And then the second piece, it would go and hit this term, and it would cancel with the denominator, and I would just get the delta y squared that we've got here. So I've sort of forced this delta x squared out. And this is the same math we did a minute ago. I can rewrite this as 1 plus the delta y over delta x. They were both squared, so squared. And this piece, it's being both squared and square rooted. And I can kind of pull it out over here. And all we're doing now is essentially treating these pieces as replace them with dx and dy instead, which is sort of the analogs for what they represent anyways. If you come back up to this picture here, the delta y is going to be similar but not exactly the same as sort of the dy, which would be, if we followed the straight line here, that distance. It would be the height of the tangent line at this point here. So I'm going to erase that now, but again, in the limit that those 2 points move together, delta y and dy become the same thing. Delta x and dx become the same thing. So this is the idea. We started with just a triangle, and now when we take a limit, we replace the deltas with dx and dy. They become the same thing in that limit. And notice that this form is exactly the same as the form of our integrand that we've got right here. So that's all I'm suggesting, is that there's our picture. Here's kind of how you can think of where this formula comes from. This formula is just a rearrangement of the Pythagorean theorem. That's all it is. We're trying to find the length of the hypotenuse using the two legs of the triangle. It's only an approximation of our curve, which does whatever, but that approximation becomes exact as delta x and delta y shrink down to a single point, and we can replace them with dx and dy. So hopefully that makes some sense. It's really more of almost a mnemonic device to remember this formula by. Okay. Now that we've got this picture and this formula, now let's do some examples and actually use it. So let's do some examples using our formula. Let me find a good one here. Let's do this one. I want to find the arc length of f of x given by the natural log of the secant of x on the interval from 0 to pi over 4. Okay. Some of these will be a little bit contrived. This looks like a weird one, until you realize that the whole idea is we wind up needing to find f prime, because that's what goes in right here into the formula. So we're going to have to take a derivative and plug it into this and wind up with this really ugly integrand. And so this can be difficult to do. We're going to get some integrands that are ugly. And so a lot of the times the original problem that we're going to start with is something where that integrand is ultimately something that our techniques of integration will work on, and we won't need to resort to jumping on a computer and doing a numerical approximation or something like that. So keep that in mind. Our goal is to plug into this formula. Integral from a to b of the square root of 1 plus f prime of x squared dx. That's it. And again, you can write this in Leibniz notation as dy dx if you prefer. But here's our f of x. We need f prime of x. So let's start with that. We need to find f prime of x. And our f prime of x is going to be equal to the derivative d dx of the natural log of the secant of x. This is a chain rule problem. So I'm taking the derivative of the natural log of stuff. There's some stuff in here. So this is the way that I like to think of, again, chain rule. If you were in my class in the past for Calc 1, this will seem familiar. If not, I think that's the easiest way to think about chain rule. We're taking the derivative of log of some stuff. This inner function secant of x is just some stuff. So when I take the derivative of log of stuff, what's the derivative of natural log of some stuff? It's going to be 1 over stuff. So 1 over stuff. And that stuff in this case is secant x. Then I need to multiply that by the derivative of the stuff. So in this case, we get 1 over stuff times the derivative of the stuff. 1 over stuff times the derivative of the stuff. What's the derivative of secant? It is secant tangent. So I've got 1 over secant of x times secant x tangent x, which is that derivative. The secants are going to cancel, and we just wind up with tangent of x. And that gives us, for our integral, that our arc length integral is going to be the integral from 0 to pi over 4, and again, those bounds of integration just come from right here. There are coordinates where we are starting and stopping our integral in the x direction, of the square root of 1 plus f prime of x. We just found f prime of x. It is tangent of x. So tangent of x squared dx. Okay, so this is looking ugly still, but luckily this piece right here, 1 plus tangent squared of x, this can be replaced with secant of x. This is our Pythagorean identity from trigonometry. So again, it comes from the idea that sine squared x plus cosine squared of x equals 1. And if I take those and divide them all by cosines, so cosine squared of x, cosine squared of x, cosine squared of x, we divide them all by cosine squared of x. This first term is just going to be tangent squared of x, right? Sine over cosine is tangent. This second term, cosine squared over itself, is 1, and this last term is secant squared of x. So this is all I'm using. I'm replacing this 1 plus tangent squared with the 1 plus tangent squared. It's just going to be secant squared. So that's how I'm going to rewrite this. The integral between 0 and pi over 4. And we just have the square root of secant squared of x dx. It looks scary. It's looking less scary now. We take the square root of the square, and this is simply the integral of secant of x dx. And this is one that we've done a couple of times. We talked about it back when we were doing the trig integrals. These ones are those ugly ones, probably just worth having memorized. This one is simply the natural log of the absolute value of secant of x plus tangent of x. And we're evaluating that between 0 and pi over 4. So this is something that is probably good to just have memorized or come from an integral table. And it's not something that we want to have to derive by hand. This is an ugly, ugly one to derive by hand. If you go back and watch the video, one of the videos from, I don't know when that was, week 3 maybe, I want to say, you can do that. We do this problem here, and it's ugly. So I'm not going to do it again now. So we'll plug in our bounds of integration, and we'll wind up with, in this case, so the natural log of the absolute value of the secant of pi over 4 plus the tangent of pi over 4. And then we'll subtract off the lower bound, so minus the natural log of the absolute value of secant of 0 plus tangent of 0. And now we just need to figure out what these values are based on, hopefully, our recollection of the unit circle. These are values that we should be able to figure out without too much trouble. So let me draw the unit circle real quickly, or at least the relevant quadrant of it. Just to give people a quick refresher. So here's the portion of the unit circle that we care about. Here's x, here's y. And this is an angle of 0 down here. That's going to be where our lower bound is. It has a radius of 1 because it's the unit circle. And the other angle is pi over 4. Pi over 4 is a 45-degree angle. So that is coming out right here. So there's the angle 0. There's the angle pi over 4. And for these angles, the coordinates are, again, as you break this down into right triangles, the x-coordinate corresponds to cosine. So if this is our theta, we have cosine of theta on the x and sine of theta on the y's. And we just need to remember the coordinates of these points. This first one is at the point 1, 0. And up here, this is at root 2 over 2, root 2 over 2. So these are the coordinates of those points on the unit circle. Again, the x-coordinate corresponds to cosine of theta, and the second one, the y-coordinate, corresponds to sine of theta in both cases. So it's always cosine comma sine. And now we can come and plug all of these various values in, right? Secant is the same as 1 over cosine. So secant of pi over 4 is 1 over the cosine of pi over 4. So it's 1 over this number right here. 1 over root 2 over 2. Tangent of pi over 4 is going to be sine over cosine. So again, let's get these all on the screen at once. Sine over cosine, that's just going to be root 2 over 2 over root 2 over 2. So root 2 over 2 over itself, anything over itself is 1. We now go down to this point, the argument 0. The secant of 0 is 1 over the cosine of 0. What's the cosine of this angle 0? Well, cosine is 1, again. Again, we're plugging now theta equals 0 in these cases. We get cosine is 1. So the secant of 0 is 1 over cosine of 0, which is 1 over 1. This is also a 1. And tangent of 0 is going to be sine over cosine, which is 0 over 1. 0 over 1 is 0. And so we've got all these values, and we can rewrite them a little bit. They're a little bit ugly. But looking at this one, instead of having a fraction within a fraction, I will multiply top and bottom by the reciprocal, basically. So or another way to think about it is instead of dividing by this fraction, I will multiply by the reciprocal. I will get 2 over root 2. So we get the log of the absolute value of 2 over the square root of 2 plus a 1 minus, for the second term, we get the natural log of just the absolute value of 1. Cleaning this up one last time. If I rationalize the denominator here, multiply by root 2 over root 2, we'll get 2 root 2 over 2. This whole thing is just going to be a square root of 2. So 2 over root 2 is the same as the square root of 2 once you rationalize the denominator. I'll let you do that on your own if you don't believe me. Plus 1. And then what is the natural log of 1? The natural log of 1 is 0. So I'm going to leave that turn off entirely. And there is our final answer for this problem. The natural log of, in this case, the absolute value can be dropped because it's positive anyways, but you can leave it there. I don't really care. Root 2 plus 1. The natural log of root 2 plus 1 is the arc length of this function on that interval. That is the distance. Okay. Let's do another one. So as a second example, I want to find the arc length of the following. Let's do a curve given by x equals 2/3 times y minus 1 to the 3/2 power on the interval from 1 to 4. So this is one of those cases where instead of y as a function of x, I have x as a function of y. So this interval itself must also imply that these are y values, not x values. So we're going from a height of 1 up to a height of 4 along whatever this curve is. Okay, so same thing. This plays the role of our g of y. The first step in finding L is it's going to be the integral from c to d of the square root of 1 plus g prime of y squared dy. So we need to find g prime of y. So if g of y equals 2/3 y minus 1 to the 3/2, then what is g prime of y? What's the derivative? So I'm taking the derivative with respect to y. This is just power rule. The power will come down. So we'll get 3/2 times 2/3. Those will cancel. And the power here goes down by 1. And we wind up with, so we'll have 3/2 times 2/3 y minus 1. And the power goes from 3/2, goes down by 1. And what does that give us? 3/2 minus 1 is just going to be a power of 1/2 up here. This piece is just going to be, and again, this cancels, it cancels, and we just get y minus 1 to the 1/2 power. So this is just the square root of y minus 1. Okay. So there's that ugly piece. Plugging this in, our arc length is going to be the integral from 1 to 4. Again, the bounds of integration I just got from earlier in the problem. And we've got a big square root of 1 plus the square root of y minus 1 squared dy. You'll notice that to do a lot of these problems by hand, you're going to wind up getting things like this. It's really, really convenient if we can get a square root in our derivative term, because the first thing we have to do to our derivative term is square it, and it'll get rid of that square root. And so you'll find that there's actually a lot of these problems that are kind of, in order to be able to do these by hand, in order to get integrands we can actually solve, they're going to look weird. They're going to look contrived. And it's all so that the integral that we get here is something that you guys can actually do by hand. In real life, they won't all be contrived, but you would get integrands that you can't necessarily integrate using our normal pencil paper techniques, and you would just have to get numerical approximations of these arc lengths. You'd have to use a computer. So the whole point of this was to avoid doing that. I'm taking the square root, I'm squaring it, they'll cancel each other out. I will have the integral from 1 to 4 times the square root of 1 plus, again, after I've squared that square root, I'll just have y minus 1 dy. I have a plus 1, a minus 1, they cancel, and this whole thing just boils down to the square root, or sorry, the integral from 1 to 4 of the square root of y dy. Lo and behold, that's something we can do. What is the integral of the square root of y? Well, that's the same as y to the 1/2 power. When you integrate, it'll go up. The power will go up 1, so it'll wind up being y to the 3/2 power. And to make up for that 3/2, I need a 2/3 out in front. And we're evaluating it between 1 and 4. And we plug those values in, and we get 2/3 times 4 to the 3/2 minus 1 to the 3/2, which is just 1. 1 to any power is just 1. We can do this one here fairly easily. I don't even need a calculator. I can either so whenever we have a fractional power like this with a number here, we can either, you want to think of the number in the numerator as being a power that we're taking it to, and then the number in the denominator being like a root that we're taking. So basically we're taking it, we're cubing it, and then we're square rooting that result. But you can do it in either order. We can also square root and then cube. And so more often than not, rather than cubing it and then taking the square root, it's going to be easier to square root it and then cube it. Square rooting it will make it a more manageable number, and we'll be cubing a manageable number. So the first thing I will do is take the square root of 4 to take care of the 2 in the denominator. The square root of 4 is 2, and then I need to cube that. 2 cubed is 8. So this is just going to be 2/3 times 8 minus 1. 8 minus 1 is 7. 7 times 2/3. This whole thing is just 14/3. That is the arc length of this function between those two y values. So again, I just want to point this out. These arc length problems are hard. They give you hard integrands. And so a lot of the problems that we're going to be dealing with are contrived to kind of simplify in such a way that we wind up with a manageable integrand. Every one of these integrands is going to have this big square root here. So that makes it hard enough. The square root, we found a way to get, if we can get what's in here to be a perfect square, stuff simplifies. Like sure enough, that's exactly what we did right here, right? The stuff in the square root became a perfect square. We were able to cancel the square root with the square and get a function that we actually know how to integrate. So you'll see this will be kind of a common theme as you do these problems in the homework. You will often have a problem that winds up giving you some sort of perfect square inside this square root that allows you to cancel the square root and that perfect square and simplify things and give you an integrand that you can actually handle. So just keep that in mind. That's not a phenomenon that happens much in real life. It's just meant in these homeworks to give you integrands that you can actually deal with. In real life, you would have you could do this for any function. You will simply wind up with integrands that we do not have analytic techniques to be able to find the integrals of. Basically, you can't do normal pencil and paper techniques that we've learned to get the answers. And it's not that you can't, it's that in many cases, no such technique exists, and we wind up having to do the whole thing computationally. So just keep that in mind. Okay, so now that we've done a couple of these, I want to move on to the idea of an Arclength function. And it's going to be doing the same basic idea of what we've been doing. But instead of specifying, again, as I mentioned before, instead of specifying both a lower bound and an upper bound for our integration, I want to be able to do it from a starting point to an arbitrary ending point. So I want to have that be a variable. So the gist of the idea here is often we're interested in finding the length of a curve from some starting point to any other point on the curve. And that is going to be a function of where that other point winds up falling. So we may want, in fact, we'll often want to find the arc length from some starting point to any other point on the curve. So if we have a curve, we're going to call that curve C, and let's make it a nice smooth one. So if a smooth curve C, and smooth is an important concept in calculus. Let me just mention this. I won't go into detail. You'll go into a lot more of detail of this if you take more advanced math classes. But smooth actually has a technical meaning when it comes to calculus. The smoothness of a curve has to do with the derivative, right? If I give you a graph like this, or even something like this, the curve is smooth along all these points, but then suddenly it has a cusp, and then it's smooth again along all these points. The idea is the derivative will exist everywhere on these curves except for right here where we have this cusp. The derivative is undefined at a cusp like this. So it's basically sharp. There is no slope at that point when it has a cusp like that. So technically, for a curve to be smooth, what it means is the derivative has to be continuous. We have to have a derivative that is continuous. Notice right here, we have a derivative that is positive, 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 because the slope is positive, and then immediately after the cusp, the slope is negative. So we go from a positive number to a negative number. That is a discontinuous derivative, and it's undefined at this point. That would be an indication that these curves are not smooth. So we're not dealing with curves like this. We need to be dealing with smooth curves, meaning the derivative is continuous. And that is exactly why, way back up here, that's exactly why we had this particular definition right here. If f prime of x is continuous, that's what guarantees that the original curve f of x is a smooth curve. So just coming back to this, if f prime of x is continuous, that's the exact same thing as saying that the curve itself is smooth. So this is another wording of that same concept. So if we've got a smooth curve C, meaning f prime of x is continuous for that curve, so if a smooth curve C has an equation, so if it's given by y equals f of x with a less than or equal to x less than or equal to b being some interval on where we care about it, then what we're going to do is we're going to let s of x, so s, then that's a lowercase s, just FYI, in case it's unclear in my handwriting. S of x is going to be the distance along that curve from some initial point to an arbitrary point x. So S of x is going to be, we're going to let S of x be, let me get my grammar right, let S of x be the distance along C, so the arc length, the distance, the length along the curve from some initial point which we'll call our P0, and it's going to be at the point a comma f of a, right? So we're starting at x equals a, and I want it to go to another point. So from that initial point to some other point, and the book uses q here, which is going to be the point x comma f of x, some other point on the curve. In this case, s is a function. So then s is a function called the Arclength function. And is given by the following. So s of x is going to be the integral from a to x, right? Our starting point was a, our ending point was x. We started at the x coordinate a, we're ending at an x coordinate of x itself. And it's going to be the integral of 1 plus f prime of, I can't do x anymore because x is now our variable, so I need a dummy variable in here, and we will use t. So f prime of t squared dt. And the name of the variable that we use here doesn't matter. It doesn't have to be t. It could have been theta. It could have been whatever. But t is a very common one that you will see, probably the most common dummy variable to use. But keep in mind, this is kind of the idea of essentially fundamental theorem of calculus stuff. When we actually take this integral and plug in the bounds, right, the t is going to disappear from the equation because it's going to be replaced with either a or x when we actually evaluate this integral at the two endpoints. And so what we'll wind up with is wherever a gets plugged in, that's just going to be a constant. Wherever x gets plugged in, that's going to make the result of this something that still depends on x, and that's what makes it a function of x. You pick a different x value, you'll get a different arc length. And so that's all it's saying is s of x is the integral from some starting point, a, here's some ending point b, and depending on where I put x, different values of x, so different x coordinates, I'm going to get different arc lengths. So depending on which value of x we pick, you will get a different arc length s, and that makes s a function of x. It depends on the x value that we choose. That's all this is saying. So these are all, again, a very long, complicated paragraph explaining that exact idea. That's all it's saying. One other nice thing about this is that oftentimes we're going to be interested in computing a rate of change of s with respect to x. So basically, as you change x, how quickly is the arc length changing? And that requires us to take a derivative. So the rate of change of s of x with respect to, so WRT just means with respect to x, is going to be the derivative. So it would simply be ds dx. But what happens when you take a derivative of an integral like this? Again, our fundamental theorem of calculus says if we take dx of the integral from a to x of the square root of 1 plus f prime of t squared dt, this is the fundamental theorem of calculus, back from Calc 1. The derivative and the integral basically cancel with each other, and this bound winds up going and replacing the dummy variable. And so we wind up just getting square root of 1 plus f prime of x squared. Or, alternatively, if we write it in Leibniz notation, square root of 1 plus dy dx squared. This can be kind of nice because if I compare these pieces over here, we can get an expression for ds, and this is going to be useful because down the lines we're going to actually want to integrate things with respect to arc length. This is something that I've had to do in my research. When I was in grad school getting my PhD, I had to integrate things with respect to arc length. I had to integrate in a space where I was restricted to the surface of some curve or some object, and I defined that surface of the object using a curve, and all of my integration, all my calculus had to be done with respect to arc length. And so if I solve for ds, I can just multiply both sides by dx, and we get an expression that looks like this. So this is some tiny bit of arc length. And we now have an expression for that tiny bit of arc length. How does that tiny bit of arc length compare to basically this function that we've got, and it's being multiplied by a tiny bit of the length x. So this is meant to be a times. We'll write it really bold so it looks, that's meant to be a multiplication symbol. Tiny bit of regular length in the x direction. And what we'll find is that, just to give you a little of intuition for this, to think about what this is telling us, what if my curve looks like this? So as a quick sort of just thought experiment, you don't need to necessarily do this, but if this is our x and y axis, and here's two curves. Here's one, goes like that. Some y equals f of x. here is some point A, and then maybe here's a second curve that's doing something like this. Some y equals g of x. And again, here's its starting point. They all start at A. How does the arc length of this lower curve, the y equals f of x, compare to, so if I change and go a tiny distance in the x direction, so if I go some delta x, and you think about it as a tiny distance, how does that compare to the change in arc length, which is our delta s, so to speak? How do they compare? Well, in this case, the two lines are parallel, and they're both just straight lines. So delta s is exactly the same as delta x whenever I have this nice horizontal line like this. This line might as well just be the x-axis. If I move 1 unit in the x direction, I will increase the arc length by 1 unit. Coming over here to our formula, this is the relationship that we're looking at. If I change dx by 1, this will also change by 1 because what is the slope of this curve? Well, it's totally flat. It's horizontal. The slope is 0. So if I plug in 0 here for the slope, I'll get the square root of 1 plus 0 squared, which is just the square root of 1, which is just a factor of 1. The factor, this function that relates a change in x to a change in s, in this case, it's a factor of 1. And that happens whenever our curve is horizontal, whenever it's moving the same direction as x. But what happens is a curve starts to get steeper and steeper and steeper. So what if I compared over here? If this was my delta x, and instead of comparing it to this bottom curve, let's go up and compare it to the top curve. So now I'm going from here to here. Right, so here is the, if I went horizontal, that is still delta x, but this distance is my delta s. And which is bigger, delta x or delta s? Well, you can see clearly this is kind of close to the same length. The change in arc length is going to be close to the length of the hypotenuse of that right triangle, and it's clearly going to be bigger. And again, we talked about it before. This thing here is an expression for the hypotenuse, right? That's exactly what we did way back here in this drawing. That was my argument, is that this piece in the integrand is analogous to the hypotenuse here. And so you can see if I change this 1 unit, this is going to change by more than 1 unit. The delta s is longer than the delta x. How much longer? By a factor proportional to whatever this, essentially this hypotenuse of this right triangle is. What's going to make the difference get bigger and bigger? The curve getting steeper and steeper. The steeper the curve is, so if the curve is really steep, right, then a tiny change in the x direction, a tiny delta x, will still correspond to a very large delta s. And that gets worse and worse. That discrepancy gets greater and greater the steeper the curve gets. So where the curve gets really steep, this function will start to produce large values, which makes sense, right? When a function gets steep, this slope will start to increase, and we will wind up getting a larger factor relating a change in x to a change in s. So conceptually, that is what's going on in this picture. That's what we're talking about when we talk about arc length, and we're writing it in terms of x. So just keep that in mind. It's going to be sort of a useful thing. We'll use this formula some down the line, but for now, we're pretty much going to focus on examples more like these ones that we did up here. So I don't necessarily want to do any examples of this. I really just wanted to highlight all of this for this really, in my mind, a very good conceptual discussion of what's going on in the relationship between what happens when you change x a little bit, how does that affect the change in arc length of the curve. And hopefully that discussion makes sense. If you can remember the Pythagorean theorem, and think of this essentially as a bunch of little right triangles, this concept will make a lot of sense.